We see temperature readings everywhere. The weather app on your phone, the oven, your car, everywhere. But when you get into the world of science and industry, getting that number exactly right, well, that's a whole different ballgame. It's a surprisingly deep and fascinating challenge. So today, we're going to dive into the science of what it really takes to get an accurate temperature reading. So you probably think measuring temperature is pretty straightforward, right? You just stick a thermometer in something and poof, you get a number. But what if I told you that most of the time, that number you're seeing isn't actually the real temperature? Yeah, there are all these hidden factors and super common mistakes that can throw your measurements way, way off. And believe me, this isn't just some academic thing for a lab. Out in the real world, in manufacturing, in aerospace, even in making the food you eat, an error of just a few degrees can be the difference between a perfect batch and a total disaster. The stakes are incredibly high, which is why getting this right is so, so important. Okay, so let's jump right in and pull back the curtain on the biggest issue, the one that most people completely overlook when they're measuring temperature. Understanding this is the key to everything else we're going to talk about. It all boils down to one word: accuracy. And all that means is, how close is the number on your screen to the actual physical temperature of the thing you're measuring? That little gap between what the sensor says and what's really happening, we call that tolerance or error. And here's the kicker. Every single temperature sensor, right out of the box, has some amount of built-in error. None are perfect. So if we know every sensor has this little bit of error baked in, how much are we talking about? How do we even measure it? Let's decode what tolerance really means, especially when we're talking about the workhorse of the industry, the thermocouple. Turns out, not all new thermocouples are created equal. Far from it. They're actually sorted into two different grades. You've got your basic, standard limits of error grade, and then you have a premium version called special limits of error, which are manufactured to be much, much more accurate from the get-go. To really see what this means, let's do a quick and dirty calculation. We'll take a super common sensor, a standard type K thermocouple, and see what its potential error looks like when it's trying to measure something that's 800 degrees Fahrenheit. All right, so the temperature we need to measure is 800 degrees Fahrenheit. Simple enough. Now, the official industry standards say that a standard type case sensor in this heat has a built-in tolerance, or error, of plus or minus 0.75%. You run that simple math, and what do you get? A potential error of plus or minus 6 degrees Fahrenheit. Now think about that for a second. That means your screen could say 800 degrees, but the real temperature could be as low as 794 or as high as 806. That's a massive 12-degree window of uncertainty. And this is exactly why your choice of sensor matters so much. Look at this. If we had just started with that higher grade special limit sensor, its tolerance is much tighter. The math gives us an error of just plus or minus 3.2 degrees. You've literally cut your potential for error almost in half, just by choosing the better tool right from the start. But it's not just about getting a high-grade sensor. It's about getting the right type of sensor for the job you're doing. Using the wrong kind of thermocouple is a classic mistake. So let's run through the main options real quick. First, you've got what we call the base metal thermocouples. These are your everyday workhorses. Type K is the king. It's cheap, it's reliable, it covers a huge temperature range. But you have to watch out for a weird thing called green rot if you use it in a low-oxygen environment. Then there's Type J, which is another popular one, but one of its wires is made of iron, so it can actually rust. And Type T, that's your go-to for really cold stuff, like cryogenics. And then you have the specialists. These are often called noble metal types, and they're for when things get really extreme. Types S and R use platinum, so they're super accurate at crazy high temperatures, but they're also delicate and easily contaminated. Type B is even more stable at the highest temperatures. And then you have the beast, Type C, made of tungsten. It can go all the way to 4,200 degrees Fahrenheit. But, and this is a big but, you have to use it in a vacuum. If it touches open air at that temperature, it's instantly toast. Okay, so you've picked the perfect high-grade sensor for your job. You should be good to go, right? Well, not so fast, because even the best tool in the world will give you garbage data if you don't use it correctly. So let's talk about the most common mistakes that you absolutely need to avoid. Here are 4 game changers. Number 1, proper immersion. You have to stick the sensor in deep enough. The rule of thumb is at least 7 to 10 times the probe's diameter. If you don't, the metal sheath can actually pull heat away from the tip and give you a reading that's way too low. 2. Protect the cold junction. That's just the spot where the sensor wires connect to your meter. If that connection point gets hot or cold, that temperature change gets added directly to your reading as error. 3. Isolate from electrical noise. Thermocouples create a teeny tiny voltage signal. If you run those wires right next to big power cables, that electrical noise can completely scramble the signal. And finally, number 4, account for degradation. Sensors are not immortal. Over time, especially in high heat, they wear out, they drift. You have to check them and replace them on a regular schedule. All right, if you follow all those steps, you pick the right sensor, you use it correctly, you're going to get a very, very good measurement. But if you need absolute precision to master your system, then we have to talk about the final piece of the puzzle, and it's the one most people get wrong: calibration. Now, this is so important because there's a huge misconception out there. Most people think calibration means you're fixing or adjusting a sensor to make it read perfectly. That is not what it is. Calibration is simply the process of taking your sensor, putting it in a perfectly known temperature, and then precisely documenting its error. You're just figuring out exactly how far off it is. So you might be asking, what's the point? Well, here's the magic. Once a calibration lab gives you a report that says, hey, at 500 degrees, this specific sensor reads 1.2 degrees high, you can't change the sensor, but you can go into your digital meter and program in a negative 1.2 degree offset. By telling your instrument to subtract that known error, you effectively cancel it out. And just like that, you are measuring the true temperature. And this is why, for the highest level of accuracy, you always calibrate the sensor and the meter together as a complete system. And really, that brings us right to the core of it all, summed up perfectly by the legendary computer scientist Grace Hopper. In any critical situation, all the guesswork, all the expert opinions, they all just fade away when you have one single, verifiably accurate piece of data. Getting that number right isn't just a technical detail, it is the absolute foundation of knowing what's really going on.